Thank you for the invitation. I'm excited to give a talk at an IPAM workshop. My lab, at Stanford, I'm the director of the Autonomous Systems Lab. My lab broadly focuses on the design of a planning decision-making algorithms for robot autonomy. That is on how to make robots capable of making decisions on their own. A key application domain of my work is space robotics. And specifically, before joining Stanford, I was a research technologist at NASA JPL, and I work on the optimization of the entry, descent, and landing of rovers on the Mars surface. Currently, through a collaboration with NASA Ames and Professor Mark Kutkowski at Stanford, we're working on planning and control techniques to grasp objects in space. Here I'm showing, for example, tests at NASA Ames, where zero gravity is emulating by using air bearings over a very flat granite table. The arms are equipped with gecko-inspired grippers. That is, grippers that, by exploiting directionally aligned microfeatures, become adhesives when loaded in shear stress. So this is a very useful property for grasping objects in space. A flight-qualified version of this gripper that you can see on the right has been sent to the International Space Station in July 2019, and we plan to do experiments on board the International Space Station at the beginning of 2021. In all these space robotics applications, increasing the level of autonomy represents a key challenge due to the coupling of the uncertainty in the environment with the typically difficult dynamics of objects in space. However, as a redeeming factor, space robots do not have to deal with intelligent forms of life, that is, humans. And indeed, interacting with humans represents a key challenge for robot autonomy. And the main topic of this talk will be indeed on how to enable in robots the capability of seamlessly and safely interact with humans. Consider in particular the case of autonomous driving, even though the work that I'm going to talk about today applies more broadly. In general, driving entails very complex interactions. For example, here, where we see some vehicles that are trying to merge on the highway, we can see that even though the overall goal is clear, there are some vehicles that are trying to join, to merge into a highway. The way that the interaction will play out is highly uncertain. And it depends on a very complex negotiation that at times could be also quite aggressive. In other words, merging into traffic and more in general autonomous driving is really an exercise in negotiation. And autonomous robots should be able to perform such negotiations for safe and efficient driving. Specifically, I like to refer to the capability of performing negotiation as a proactive decision-making, whereby a robot should be able to proactively interact with other agents to infer their intents, while concurrently exploiting this information to take actions that account for agent responses. Now, my key approach to enable proactive decision-making is model-based, whereby a probabilistic understanding of the interaction dynamics is used as a basis for policy construction. This is in contrast to model-free approaches, whereby human action possibilities and associated likelihoods are only implicitly encoded in a control policy that is learned from data. And the claim is that by decoupling action-reaction prediction from policy construction, we can achieve a level of transparency in the design that is difficult to achieve with model-free approaches. Now, the first step in a model-based approach for proactive decision-making is to come up with a good model that allows us to predict the intent of a human. My work in developing such a model is guided by three key considerations or principles. First of all, we want to, from the point of view decision-making, we want to produce a model of human intent that allow us to predict what a human will do in the future, conditioned on what a robot could do as its next move. Second of all, we're targeting a decision-making problem with a time scale of about 1 second. This is very different from a traditional decision-making under uncertainty problems, whereby you reason over multi-second type of decisions. And this is also different from low-level control, where you reason at the millisecond level, for example, in the context of a collision avoidance. So it is a gray area between decision-making and low-level control. Finally, a third, at this level of decision-making, uncertainty is generally multimodal, corresponding to the very different features that a human might display. For example, in the example on the right, I'm showing a human that is trying to change lane with a robotic vehicle. And so a question that a robotic vehicle might ask is, where if I were to accelerate, what could be the reactions from the human? In this case, the distribution is inherently multimodal. There may be some probability mass around the reaction whereby the human is going to decelerate, so the human is nice, or the human is aggressive and is going to accelerate. So these are two drastically different modes that need to be captured when we do intent inference. Fourth guiding principle, prediction should be history dependent in order to uncover latent behavior such as aggressiveness or alertness. And finally, we would like to have a decision-making module that is as interpretable as possible in order to have high confidence in its behavior and also to ease debugging. Now, to infer human intent, typical approaches such as inverse reinforcement learning, which I refer to as ontological or theory of mind approaches, postulate some structure on how humans make their own decisions. For example, in terms of a cost function that we postulate humans are trying to optimize. But this postulated structure is oftentimes difficult to reconcile with how humans actually behave. Humans are not cooperative, but they're not adversarial in general. And such a fuzziness of behavior is difficult to reconcile with a theory of mind approach that ultimately is rooted in game theory. We have thus investigated whether with enough data, we can reason about relative likelihoods of human actions and responses without making any assumptions on how humans make their own decisions. I refer to this approach as a phenomenological approach, in that we do not postulate any structure, but rather we try to predict what a human could do in the future without reasoning about underlying motivations. This is a phenomenological approach, is more data hungry. You need more data to train these models. But the claim is that actually we can have, in the end, a much more expressive model. Specifically, there has been a lot of great work from the generative modeling community about how to predict the future. The way that our work differs from a traditional prediction work, for example, from the machine learning community, is that we are interested in predicting the future, not only conditioning on past observations, but also by taking into account what a robot could do in the future. So basically, we want to predict what a human might do in the future, conditional on a possible robot action. Specifically, what we want to learn is a probability distribution that allows us to predict the next human actions. UH denote here control actions by the human at the next time step, conditional on the history of the interaction. X will be the joint state, for example, relative speeds and relative position. U will be relative controls. And critically, conditional on what the robot could do at time t+1, so in the future. That's how we capture the interactive aspect of the interaction. In other words, with this model, we condition on the history of an interaction in order to uncover latent behavior, as well as on future robot actions in order to capture the interactive aspect of an interaction. In practice, we use a conditional variational autoencoder model in order to learn such a conditional probability distribution. Note that here we're not postulating any structure in terms of the human decision-making process. That's why I refer to this approach as a purely phenomenological. The way that we use this model then is as follows. In this plot, I'm showing on the x-axis time and on the y-axis longitudinal acceleration. Solid line means that something has happened in the past. Dashed lines means future. So here I'm showing that for the past 0.7 seconds, both the robots depicted in blue and the human depicted in red had zero acceleration. So they were going at a constant speed. And then the way we use this model is as follows. If the robot were to, for example, enact an acceleration, costing, and deceleration maneuver represented by the blue dashed line, what could be the possible human responses? And you see that by sampling the CVAE model, we get a bunch of possible responses. Most of them telling us that a human would decelerate, but in some cases, the human might actually accelerate. So far, I've been considering the case of pairwise interactions. In the past year or so, we have extended this framework to ingest as conditioning variables a vast set of heterogeneous data from dynamical information. Of course, a biker behaves in a way that is different from how a human driver behaves, all the way to maps encoding information such as road geometry and even human silhouettes. The result is a generative model that allows us to condition predictions on highly heterogeneous data and considering highly heterogeneous vehicles. For example, in this scene, I'm showing predictions based on information from pedestrian, bikers, possibly other autonomous cars, and conditional maps. The end result is an algorithm that we refer to as a Trajectron++. This is a forecasting model that explicitly reasons about agent dynamics and heterogeneous data. And to see the value of actually conditioning predictions on, say, dynamics of the agents or map on environment, let me show you three snapshots of simulations. In these tests are used by are done by using as data the new scene datasets, which is a dataset released by a company called autonomy, and basically comprises data gathered through operations in Singapore. So on the left-hand side, we're trying to predict what the red vehicle will do in the future, and we're using our base CVAE model, whereby we do not condition on agent dynamics about the other agents in the scene. We can see that there are some other cars and some pedestrians on the curb, and we do not condition on the map. Here we see that the prediction actually undershoots the actual trajectory. The actual trajectory is depicted in white, while the prediction is represented by those confidence ellipses in red. In the center, I show the same intended prediction problem, but now I account for agent dynamics. Here I see that the prediction modules outputs two main modes, one that now coincides with the ground truth, and another one that actually undershoots the ground truth. Finally, on the right, I condition based not only on the agent dynamics, but also on the road geometry. And now the prediction is nicely projected on the ground truth. And actually the mean matches very nicely the ground truth trajectory. So this is just one way to visually show you the importance of actually conditioning on map information, dynamics information, in order to have high quality predictions. Actually, this model competed in one of the challenges about intent prediction. It was one of the top 3 models in the competition amidst dozens of models. All the data and the code is available online on our GitHub. So the key takeaway from this first part of the talk is that phenomenological models, in particular deep generative models, achieve state-of-the-art performance. But in my lab, we are interested in decision making. So how do we use these generative models from the perspective of a decision making? So what we do is to, in the context of autonomous driving, look at the motion primitives for the robotic vehicle. We typically look at about 4,000 motion primitives. A motion primitive could be a trajectory whereby we first accelerate, then we steer, and then we decelerate, for example. And then for each one of these motion primitives, we sample the generative model to see what could be the possible action responses. In actuality, we sample about 100,000 action responses for the human per planning cycle. We can do that at about 4 Hertz by using an implementation in GPU. This is, of course, all of this is highly parallelizable. Then what we do is to score the best action, select the best action sequence, drive the first chunk of it, and then repeat the process in a receding horizon fashion. In order to score which motion primitive is best to drive, we consider an aggregate cost function where we have different reward terms, and we take an expectation with respect to all the possible human responses. Critically here, we take an expectation of such a stochastic cost. But we do have actual distributional information about what the humans could do thanks to our generative model. So something interesting to do would be to actually go beyond an expectation operator that basically encodes a risk-neutral assessment of a stochastic cost, and actually use a risk measure that also accounts for tail events, for example. Now, how to go from a risk-neutral formulation to a risk-aware formulation where we swap the expectation with the risk measure is a fascinating topic. There are a number of interesting aspects, both from a computational standpoint and modeling standpoint. I won't be discussing them here, but if you're interested, I wrote with one of my former postdoc, Annie Majudmar, now at Princeton, a sort of a position paper about how to encode risk in stochastic decision-making for robots. Instead, what I'm going to do now is to show you how everything works together. Specifically, I'm going to consider a task whereby there is a robotic vehicle and a human vehicle, similarly as before, and the task is to swap lane. This is a human-in-the-loop test whereby the human-operated vehicle is driven by a student by using a software called Virus VTD, while the robotic vehicle is driven by our algorithms. As I said, the task is to swap lane. On the left-hand side, you can see predicted human responses in terms of longitudinal acceleration and longitudinal velocity for a given candidate motion primitive for the robot. As you will see, the interaction, as a reminder, the blue vehicle is the human one and the white vehicle is the robotic one. As you can see, the interaction is quite natural. There are some interesting behaviors that emerge. For example, the robotic vehicle nudging a little bit on the other lane in order to disambiguate the intent of the human-operated vehicle. So this is great. Until disaster happens. So this is a case whereby one of my students decided to swerve into the robot for whatever reason, and basically acted in a way that defied the predictions of the intent prediction module, and consequently, there was an accident. I would claim that with probabilistic decision-making, this is actually unavoidable. First of all, probabilistic guesses are still probabilistic, and therefore sometimes we might guess it wrong. Second of all, at this level of the decision-making hierarchy, we incorporate collision avoidance as an additional penalty term amidst many other penalty terms. And this can cause some conflicting objectives. And finally, as I said before, we do replan at about 3-4 hertz, which is quite fast, considering the fact that we're doing decision-making under uncertainty, but it's still ultimately too slow to ensure safety. Which leads us to a key question. How do we integrate safety assurances within a probabilistic performance-centric planning framework? More explicitly, the big challenge is how to strike the right balance between safety and efficiency. High-level planners, like the one that I just showed you, typically leverage a probabilistic reasoning in order to promote efficiency at the cost of safety. While low-level planners typically reason in a worst-case manner in order to promote safety at the expense of efficiency. Which leads to this conceptual plot. On the x-axis, I have efficiency. On the y-axis, I have safety. High-level planners are very efficient, but not very safe. Low-level planners are very safe, but not very efficient. If you want to be super safe, you should stay home. You should not go anywhere. The ideal would be to be maximally efficient and safe, but that is probably not attainable. So the question is, how do we properly balance safety and efficiency, and how we can push basically the green bubble that you see in this plot? Explicitly, the key challenge is really how to glue a high-level probabilistic planner with a low-level safety controller. And I would claim that this combination is often overlooked in academic research. That is, people really work either on stochastic decision-making or on motion planning, but how to actually mix these two levels of the control hierarchy is always a sort of leap of faith and relies on heuristics. So what I'm going to do now is to show you a way that we have developed to enable such a gluing. Specifically, I'm first going to focus on the low-level collision avoidance module, and then I'm going to discuss how this new low-level collision avoidance module can be integrated in a probabilistic decision-making planner, like the one that I presented before or the one of your choice. As I said, let's start with discussing low-level planners aimed at promoting safety. Of course, there are several approaches to promote safety, like, for example, including potential functions, considering constraint optimization, pre-computing a library of emergency maneuvers. But the key point here is that all these methods do not account for interaction with a sentient agent, that is a human. Thus, they're difficult to glue with a decision-making module that strives to promote efficiency through smooth negotiation. So what we do in our work is to harness the tool of Hamilton-Jacobi reachability in order to reason about action-reaction responses, even at the lower levels of the control hierarchy. And Ram talked before me about reachability, so I do not have to give you a hard sell about how reachability is a useful tool. Here, I'm just going to describe how reachability is very useful in order to properly glue low-level collision avoidance with a high-level stochastic decision-making planning. And in particular, in the context of reachability, reachability is oftentimes interpreted in a forward open-loop sense, whereby the dynamics, for example, the human vehicle are propagated forward, and the resulting set is considered like an obstacle that the robotic vehicle should not get into it. This, in general, leads to a very conservative behavior by the robot. It's not really useful in practice. What we do instead is to harness the tools of backward reachability, whereby the closed-loop interaction between the robotic vehicle and the human-driven vehicle are propagated backward in time to account for the action-reaction responses in a closed-loop manner. And the resulting set basically encodes the notion of the set where you do not want to be in because there might be no action you can take to avoid an accident despite your best efforts. And I claim that this is exactly how for example, we drive a motorbike. In a motorbike, an accident usually is little. So typically, and I ride a motorbike. So I like to think that what I have in mind is a sort of a backward reachable set in my mind. I really want to make sure that I do not place myself in a position whereby I'm boxed in, which means that if someone does something erratically, I might actually collide with the vehicle. Explicitly, a backward reachable set is the set of avoid states for which there exist strategies for the human that for all inputs of the robot will lead to collision. These sets can be computed by solving the Hamilton-Jacobi-Isaacs partial differential equation, whose solution V, referred to as the value function, give us the backward reachable set as its zero sublevel set. Now, typically, the optimal avoidance control is to choose the action U star R. R stands for robot. So this is the action that offers the greatest increase in the value function, assuming worst case reactions by the human. So basically, the idea is that we want to get out of the unsafe set as quick as possible under the assumption of worst case reaction from the human. And the typical way this controller is used in reachability theory is to switch this controller whenever near the backward reachable set. So whenever you are near to a collision. So here I'm showing a simulation whereby the robotic vehicle is the red one. The green vehicle is the human operated vehicle. The yellow line depicts the backward reachable set for the robot. And here you can see that as the human swerves into the robotic vehicle switches to the Hamilton-Jacobi controller, but the result is that the vehicle stops. So this is certainly safe, but it's not very efficient. Every time there is a negotiation with another vehicle, if the robot were to stop, you will have something that is safe, but not very efficient. So it wouldn't really allow you to use such vehicles for mobility purposes, which is the ultimate goal. So the key question then is how do we remove some of this conservatism while still keeping the safety properties of backward reachability? Well, the idea is that rather than switching to the optimal avoidance controller, we actually reason in terms of safety preserving controls. Those are controls for the robot that ensure that the value function is not decreasing. So at least we do not make the situation worse. Now, this set, which is a control set, is typically leads to a highly non-convex optimization problem. So it's not very tractable for real-time control. So what we do is actually to linearize this set around the operating condition. And specifically, the low-level controller then takes the form of a relatively standard MPC controller that is used quite widely in robotics and in autonomous driving and so on, whereby the idea is to, given a reference trajectory, for example, a reference trajectory coming from the high-level planning module, come up with the controls for the vehicles, for example, in terms of steering commands or longitudinal and lateral forces. You want to minimize the tracking error along with control effort, subject to linearized dynamics for the vehicle, stable and handling envelope constraints, actuator constraints. So this is all standard stuff, but with the inclusion of an interaction, instantaneous interaction safety controller that enforce safety through the lens of a Hamilton-Jacobi reachability whenever near the backward reachable set. So basically, whenever we are close to entering the backward reachable set, so the set of states that might lead to collisions if the human were to act erratically, then we only reason through these constraints in terms of safety-preserving controls. This is a much smoother way to include the ideas of reachability without being overly conservative. Putting everything together, the overall control and decision-making module looks as follows. We have on the left a high-level interaction planner that produces nominal trajectories through CVA-based intent prediction model. On the right-hand side, we have a reachability cache that is pre-computed. Of course, solving the Hamilton-Jacobi-Isaacs equation is computationally very challenging, but the good news is that that can be done offline. And the result is a reachability cache that encodes notion of relative states that are unsafe, that is, that might lead to collisions despite our best effort. And finally, we have a low-level safe, low-level tracking controller, the MPC controller that I showed before, that executes controls that minimally deviate from the planner choice in order to ensure safety at all times. So this is basically how we do the gluing. On the one hand, we have interaction planner, high-level decision-making, reasoning probabilistically. On the right-hand side, we have a reachability cache that encodes reachability-based constraints. And then we glue them through an MPC controller. And we had to do some additional accounting in order to avoid over-conservatism. So we test this stack on one of the full-scale self-driving vehicles we have at the center that I co-direct at Stanford, the Center for Automotive Research at Stanford. So the vehicle that you see is X1, is a drive-by-wire vehicle, which is instrumented with LiDARs and computers on board and so on. That's where we run the full stack from perception to intent prediction to high-level decision-making to the MPC tracking module. And then we have a smaller vehicle that might be difficult to see right now that is next to the autonomous vehicle, which is basically an RC car that is remotely controlled by a student. And the reason why we're using an RC car as opposed to a full-scale human-driven vehicle is that basically we are testing how we can abuse of our algorithms in order and see to what extent they might avoid the collisions. So for example, this was a case whereby on the bottom left-hand side, you can see the view of the road from the top. So the red vehicle is usually the robotic vehicle. The blue vehicle will be the human-driven one, so the RC car. So here is a case whereby the RC car is driving nominally, it's going straight, but then all of a sudden the student, decides to swerve into the autonomous car. And the autonomous car smoothly gives control to the reachability controller through the reachability constraint that I showed you before. And then the high-level decision-making module recovers. So the interaction was very uneventful. And that's the point. So going back to the plot that I had before, the safety versus efficiency. These are the results from the field tests. The red dots correspond to a case whereby we only use the reachability-based controller, but we do not account for probabilistic reasoning. The blue dots correspond to the case where we only use the probabilistic planner, but we do not account for the reachability constraint. And the green dots correspond to the case whereby we merge the two through the MPC approach I showed you before. And as you can see, we can achieve a fairly good balance between being safe and efficient. And of course, there is some nuances about how we define safety and efficiency that, if you like, we can discuss later on. So the takeaway message here is that safe and efficient interaction-aware decision-making requires a principled blending of probabilistic reasoning and adversarial low-level control. This blending is oftentimes overlooked and then it's left to heuristics. But in reality, there are ways to do that in a way that is fairly principled. One way is the way that I show you today through the lens of Hamilton-Jacobi reachability. Now, I'd like to conclude this talk by giving a quick overview of a few of my current research directions related to this topic. In particular, I'm going to talk about how we can come up with representations for forecasted trajectories that are more amenable to downstream control. I'm going to talk about how to account for uncertainty sources in a trajectory forecasting that comes from the perception module. And finally, how to add a logical structure to our predictions in order to make such predictions more structured. First of all, nearly all methods for trajectory forecasting, like the one that I presented today, but many others, this is a fairly active field of research, produce as outputs individual trajectories. So basically a time-stamped sequence of waypoints. And this is a very natural output structure. On the other hand, this output structure is not the most efficient to use for downstream decision-making. For example, as I showed you before, if we just have as an output structure trajectories, now we need to basically enumerate them in order to do decision-making, which is not very efficient. So what we're working on is instead to look at representations for intent prediction that are cognizant of downstream control application, specifically through a system theoretic formalism, where the key idea is to model a scene as a linear time varying system. Here, X is the concatenated vector of states of the robot and all the other agents in the scene. U subscript R is the action that is the control for the robots, and W is a process disturbance. So just to make things concrete, in the case whereby we have one robot, one vehicle, and one pedestrian, then we will have a vector that concatenates three set of state vectors. And what we want to learn are the off-diagonal elements of the system matrix AT. And the idea is that these off-diagonal element represent agent-agent interactions and how they impact the future behavior of the scene. The blue elements, the ones in the diagonal, are actually not learned. Those represent the dynamics of the vehicles that we assume we know. We also have as control only the control for the robots, because that's the agent we control, and we want to see how the control of the robot is going to influence the future evolution of the scene. So basically, the idea is to train a CVE model that outputs a mixture of linear time varying models, where each specific linear time varying model corresponds to some high-level driving behavior. And now here you should see the advantage of this output representation. With this output representation, then we can feed it to any control algorithm of our choice, for example, MPC. So it's much more amenable to downstream decision-making. Turns out that this is a recent paper that was recently accepted at the CoRL. We can achieve pretty much the same prediction accuracy of the unstructured CVE model that I presented at the beginning of this talk, while actually dramatically improving the computational efficiency of downstream control. In general, this idea of working on representations that are cognizant of downstream control applications is a very active area of research in my lab. Second, we are specularly working on how to account for uncertainty sources that come from the perception module. For example, to understand how uncertainty propagates from perception all the way to trajectory forecasting and how we can account for that. Or, since of course perception is noisy, how to make sure, and for example, here I'm showing the video on the right, how the classification of objects sometimes might switch in a fairly erratic way. Look, for example, at the yellow vehicle. How we can make prediction more robust to the noise that is inherent in the prediction module. And finally, we are looking at how to add logical structure into our predictions. For example, to be able to condition our predictions on, say, rules of the road. Now, the key challenge here is to see how we can make logic compatible with the neural network paradigm. Well, it turns out that we have developed a framework that allows us to express signal temporal logic formula, STL, in the same computational paradigm that is used by deep learning, namely computation graphs. We plan to exploit these results in a couple of ways. First, we can jointly optimize for both prediction performance and robustness to an STL formula in order to embed structure in the neural network model. And second, for example, the fact that a vehicle should obey the rules of the road. And second, we can verify the logical properties of the model and detecting any possible anomalies. So takeaway message here is that the next generation trajectory forecasting method should really take into account of the interactions with the other parts of the autonomy stack, both upstream, for example, perception, and downstream decision making. So far, I would claim that the field of trajectory forecasting has been looking at the forecasting module in isolation without really properly taking into account interactions. All right. So as a conclusion, generative modeling is becoming a state-of-the-art tool for trajectory prediction. When we started this line of research, more or less in 2018, generative modeling was still a very recent tool. But now it's really becoming more widely adopted in the community. We do actually have a review paper that is available on arXiv, where basically we provide a tutorial on how to use generative modeling, and particularly CVA models, for trajectory forecasting. If you don't want to go through the paper, then we have a blog post which can be read more quickly. Generative modeling is very useful, as I said, but it is quite difficult to integrate within the overall autonomy stack. Thus, we're currently working on how to reason about representations that are specifically cognizant of the downstream control application, for example, by projecting predictions into a system theoretical formalism, how to integrate trajectory forecasting with upstream perception module, and finally, how to add a logical structure in order to increase the expressivity and power and interpretability of these models. That said, all our work is, all our code is available on our GitHub page. And I would like to acknowledge all my collaborators, in particular, the 3 people on the top left, meaning Karen, Boris Ivanovic, and Ash Merling, which were the main developers of all the results that you have seen today. Thank you, and I look forward to your questions.